everybody, I am making a quick video about two aspects of volume problems that come up at both Junior Cert and Leaving Cert. So I'm going to start off today with talking about Archimedes Principle. Archimedes, as you may have learnt in science, was this guy who apparently, I'm sure it's much more complicated than this, got into his bath and noticed that the water level rose. And from that he deduced that you could find the volume of an object, an irregular shaped object or any object, by putting it in water and seeing how much the water rose. So the idea being that you have this tub of water and you know how much water is in it, though it doesn't really matter how much water is in it. There's my tub, let's say it's some kind of cylinder, and then this is all water. And the idea being that if you take an irregular shaped object or any object at all, okay, there's my object. If you take it and put it into the water, so it's now there it is. If you do that, then the water will rise by a certain amount. And what he said was the volume of the object will equal to the volume of the rise in water. So you may not know the volume of the object, but if you can work out how much the volume of water changed, then you know the volume of the object. So I'm just going to pause this for a sec while I set up my example. So hopefully you can see here I have a jug from the kitchen with water in it. If we were in school, I'd use a graduated cylinder from the lab, but we're not there, so here we go. So this is a Phillips jug, which you get with one of those hand blender things. But anyway, I've put water in it. I've just tried to put the card behind it, partly to hide the mess on the desk behind it, but also so you can kind of focus a little bit on the water. So here's the water. The water's up to this level. I've made a mark with a Sharpie here. Now what happens is I have this rock. I don't actually know what volume it is. I could weigh it, but I don't know what volume it is. It's very awkward shape. I suppose I could make an estimate as some kind of rectangular solid, but it's not quite rectangular. So what I do, according to Archimedes, is that I put that rock in the water. Now there's the water there, look, just above the 200. I put the rock in the water, and if you notice, the water level rises up to here. So there it was, and there it is now. Okay, so let's just mark that. Okay, so according to Archimedes, the volume of the rock, which I've put in there, is the same as this little bit of water here. Do you see this bit? So it's the same as a cylinder of that depth. I've kind of shaded it in there before I turned it back on. So let's just go through that one more time. I'll get my hands wet here. So there it is. I'm going to regret this, but anyway, there's my cylinder of water. You can see the water is at the bottom mark, just above the 200. Can you see that? There's the water. Now, if I take my block and I put the block in, the water level rises, and it rises up to that second mark above the scribbled line. That's what Archimedes' principle is saying. So let's talk now about how that looks in a maths problem. So let's just take that cylinder we were using. Here's the cylinder. I'm just going to draw it here. This is the mixer cylinder that I was just using, the kind of jug thing. And I just measured it there, and it has a diameter of 7 centimeters. So it has a radius of 3.5 centimeters. Okay. The height of the cylinder here doesn't actually matter. Okay, the height of how tall it is doesn't actually matter. I can check it now. It's roughly, I'm looking at it there, it's about 15 centimeters. Okay, but this does not matter, because all that we're worried about in height, this does not matter, because all we're worried about in height is that we had water here. This is the water we had. We got our stone. We put it in. You saw what happened. There's the stone now resting on the bottom of the, and the water went up. Now I measured how much the water went up. This was the water going up. Remember, I colored it green. That's the difference. That was actually just 1 centimeter. So really all we're interested in is the volume of a very small cylinder of 1 centimeter height and a radius the same as the container of 3.5. The volume of that cylinder, kind of an imaginary cylinder, I suppose. It's the cylinder in your thinking. The volume of that cylinder, which is the water level rose cylinder, the volume of that cylinder is equal to the volume of the stone. So if I can find the volume of the cylinder, which I can, of course, because it's pi r squared h, which is 3.14 by 3.5 squared by 1 centimeter. If I can find the volume of that, then I will have found the volume of the stone. So 3.14 by 3.5 squared by 1 equals, so the volume of water was 38.465. I think that's a bit accurate for my level of scientific experiment this morning, so let's just say 38 centimeters cubed. So this here, 38 centimeters cubed, is how much the water changed, how much the water changed. In other words, it's how much more water we seem to have, how much more water we appeared to have when the stone went in. And the phrase that they use is displaced. That's the physics phrase. So it's displaced water. The volume, the water level rose. This is called the displaced water. So we now know that the volume of the stone is 38 centimeters cubed. Okay, I hope that makes sense. I know it's a challenging idea. It would be easier to see if we were in school, but hopefully just that physical example will help you. Now, the other type of question that they tell you is, I'll get it set up now, okay? Okay, so these next types of problems I call them plasticine problems, and I'll show you now why. They're also called remolding problems. So here I have some plasticine which I've been working on hard this morning. It's actually really hard. I guess it's a cold day. So there's a blob of plasticine. Now I don't know whether you played with plasticine or Play-Doh when you were in Montessori or whatever, but anyway, if you played at home or with Play-Doh or with plasticine, you will, or even in art, you'll know. So there is a very poor sphere that I've made out of the plasticine. Okay, if I take that sphere and I remold it, okay, and I remold it into a cylinder. There's a cylinder. Can you see it? It's a slightly better cylinder than it was a sphere. There's a cylinder. The volume of plasticine hasn't changed. All it's done is it's changed shape. So it was a sphere and now it's a cylinder, but the same amount of plasticine is there. So if the volume of the sphere had been 40, the volume of the cylinder would be 40. If the volume of the cylinder is 70 and then I remold it into a cuboid, so actually I think let's keep with 40. So we said the volume of the sphere was 40, the volume of the cylinder is also 40, the volume of the cuboid, I haven't been doing enough plasticine modeling during lockdown. There's a cuboid. The volume of the cuboid is also 40. Okay, it doesn't matter what shape it takes, it still has the same amount of plasticine. And that's the same idea of these questions that we're going to talk about now. So that's why I call them plasticine problems. So what we had there was we had a sphere which we said was a volume of 40. We turned it into a cylinder which was still a volume of 40, and we changed it into a cuboid which shows still a volume of 40. The volume does not change. The volume does not change, and that's really important. So in this plasticine problem, I'm calling it, we're told that a cylinder has a volume of 314. So I'll just write that down here. So a cylinder has a volume of 314 centimeters cubed. It's melted down and remolded into a sphere. Find the radius of the sphere. So the volume of 314, that's pi r squared h. We may not need that, but we'll write it down anyway. It's a cylinder, and they take the cylinder and they change it into a sphere. So it's some kind of metal. They've melted it down and they've remolded it, and they've got a sphere. And the volume of the sphere is also 314 because it's the same amount of metal. And that's 4 over 3 pi r cubed. So we need to find out, we're asked to find out the radius. We're asked to find out this value. So what we've been told effectively by telling us that the cylinder has a volume of 314 and they change it into a sphere, we know the volume of the sphere is 314. So we can say 4 over 3 pi r cubed is equal to 314, and we can go on from there and solve that like we've been doing already. So let's just see, I'm going to divide both, well, I'm going to multiply 4 over 3 by 3.14 first. 4 divided by 3 equals times 3.14 equals, so that's 4.186 r cubed is equal to 314. So then I'm going to divide both sides. Let's say it's 4.2. R cubed is equal to 3.14. I'm going to divide both sides by 4.2. So r cubed is equal to 314 divided by by 4.2. So r cubed is equal to 314 divided by 4.2, which equals 74.76. So r is going to be the cube root of 74.76. r is equal to cube root 4.2 centimeters. So if you had a cylinder of volume 314 centimeters cubed and you melted it down and made it into a sphere of the same volume, because you've just melted it down and taken all the metal and made it into a sphere, so it's also got a volume of 314 centimeters cubed, that sphere would have a radius of 4.2 centimeters. Okay, I hope that helps today.